streaming. All right, so I think we're ready to start. So are there any questions about a homework assignment other than what homework assignment? Any questions? So there was an earlier question, about, okay, so this is A union B, this is A, difference between A and B, and then the question asked about the membership. So what you need to do is to say the set A looks like this, the set B looks like this. It's going to be graded manually, which means, other than you have to use the correct symbols to kind of say where it begins and where it ends. As long as I can read it correctly, it'll be fine. So, any other questions? That was basically just a formatting question. What kind of format am I expecting from the answers? Any other questions about the quote unquote homework assignment? Yep. Sorry? After it is graded, yes. Yep. So I think it's due on Wednesday. So basically, on Wednesday after the due date, you'll see the answers. All right. Any other questions regarding that quote unquote quiz, which is basically your homework? Yep.
I wasn't sure about number 3 that says A in the subset of A in the set. I don't know how to say that.
Okay.
Is that a
So,
subset of A inside of a set? It's asking if it's true or false.
okay. So let me see if I can open the quiz in a preview mode. And oh, you guys cannot see it. Wrong channel. All right. That's good. All right. So we are talking about this particular quiz. And let me do a preview. I think I didn't randomize the questions, so question number 3 should still be the same. Is this the one? So it's basically just answering the question: is the expression true or is the expression false? And I cannot tell you which one it is. So you have to think about what kind of elements you can have in a set, and what this symbol really mean, the element of or in. And the notes has some examples, so you want to refer to the notes for those examples. But other than that, I cannot tell you which way it is. All right. Any other questions? Other questions? All right. So if there are no additional questions, we are going to continue with the notes. And I believe that we have completed the discussion of injection, surjection, and bijection, which means on Wednesday we're going to have another homework assignment on those concepts. So that's what we'll do on Wednesday. Not today, because I don't want to give you guys more than one active homework assignment at a time, unless it is absolutely necessary. All right. So the next topic has to do with relations. Um, I'm kind of debating whether to switch the order between these two, because the concept of aleph null actually does relate to functions a little bit more than relations. So I think that's a little bit more natural, so that we kind of talk about aleph null, which depends on the concept of relations. I mean, of functions, and then we go back and talk about relations. Are there any objection about that? I mean, I can do it either way, or we can just go ahead and just do it with relations. How many people read ahead of me, including the relations module? Okay, so that means it doesn't make any difference. Okay, so if it doesn't make any difference, I'm going to switch the order. So relations is now under aleph null, and we'll go after aleph null first. All right, so we'll go ahead and take a look at, what is this kind of really strange name? What is aleph null? So this begins with the discussion of the set of natural numbers. Now, when I took math classes, the set of natural numbers start from 0, but there are some people who say that it starts with 1. It doesn't really matter, but for the discussion in this class, we'll say that it starts with 0. So it will be all the counting numbers, 0, 1, 2, 3, 4, and so on. So are there any questions about the set of natural numbers? Is that okay? All right. And we use this kind of funny looking n, inside the bars to represent the set of all natural numbers. And then we use this even funnier looking, n, which is aleph, to represent aleph null is representing the cardinality of the set of natural numbers. And you might go like, but is that even possible? Because there's an infinite number of elements in this particular set. How can we assign a particular symbol that looks like a constant and say that, okay, from here on, aleph null, which is this funny looking symbol here, is representing the cardinality of the set of all natural numbers. That just doesn't seem very natural or even possible. So we'll talk about that later. So before we go any further, we'll talk about the set of all integers. So this fun-looking z is representing the set of all integers, positive and negative, and also 0 itself. So now the question is, how do we compare the cardinality between the set of all integers and the set of all natural numbers? Can we at least compare those two? Can we say they are the same or they're different? So these are all kind of really kind of abstract exercise in a way, because we are looking at a set that has an infinite number of elements, right? And then we say, when you count the number of elements in this particular set, is that the same as the number of elements of this other set here, which also has an infinite number of elements? That doesn't seem very easy to understand, okay? So what we're going to do next is we'll ignore this question, okay? Are they the same? Are the cardinality between the set of all integers the same as the cardinality of the set of all natural numbers? We'll ignore that for now. Instead, what we'll do is we'll start to look into functions, and that's why I don't want to put relations in between this module and what we talked about last Wednesday, because this is a very natural continuation of the discussion of functions. All right? All right, so we'll take a look at this function here. Yes, I did use the ternary operator in C and C++. How many people remember what is a ternary operator? Okay, I see some hands. How many people do not remember what a ternary operator is? Okay. How many people never had ternary operator introduced in CISP 360 or 400 or 430? Okay, it was never introduced. Okay, that's okay. That's not too hard to explain. So what I'll do is I'm going to explain it with some examples. So we'll get rid of this stuff from my earlier class. All right. So let's say I want to define absolute number as a subroutine, okay? So with absolute number, it's okay to have an unsigned as a return type, because after you take the absolute number, it's all going to be non-negative. So ABS, is the name of the subroutine, but the parameter has to be signed, because that's the whole idea. I mean, you basically flip all the negative values to the positive value of the same quantity, of the same magnitude, I should say. Okay, so without ternary operator, it depends on how you want to do it. I like to do it this way. Okay, some other professors will do it some other way, which is fine. So I just basically say if x is less than 0, we go to this branch. Otherwise, we go to another branch, and then we just say return result here, and then I just go back and backfill what is supposed to go into the then and also the else branch here. So if x is less than 0, then the absolute value is going to be the negation of x, right? Because x is negative, so in order to flip it back to the positive side, we take the arithmetic negation of x, Otherwise, if x is not less than 0, which means x is greater than or equal to 0, then the result is just x itself. It is already in the right direction. Is that okay so far? Okay? So that's one way to implement the absolute value subroutine. The other way is a one-liner. Okay? So the one-liner version, and I will make this truly a one-liner, because you can actually do it in C. It would just say return x is less than 0, negative x or negation of x, otherwise it is x, and that's it. That's the one-liner version of the absolute value function. All right, so now that you understand the one that is not using a ternary operator, let's look at this one that does use a ternary operator. So the ternary operator consists of the question mark and the colon. Okay, as the name implies, the ternary operator requires 3 components. The first component is whatever is to the left-hand side of the question mark. It is a condition. You evaluate it like a condition, just like a condition of a conditional statement. The question is it true or not? Okay, in other words, in this case, I'm asking, is x less than 0? It can either be true or false. Okay? Whatever is between the question mark and the colon is what I would call the then expression or the then value. That is the value that would become the value of the entire expression if and only if the condition is true. What if the condition is false? Then you use the third expression, which is the one to the right-hand side of the colon. That is what I call the else or false expression. Okay, if the condition is false, then we evaluate and we treat the last or the third expression as the value of the ternary operator itself, or the ternary expression itself. So it is kind of like a conditional statement in an expression, which is really cool, because you can see how my rather long original program got shrunk into one single line. And some of you go like, but Tech, this is not fair because you did not use the same style of opening new lines and putting a statement on the line. Fine, we can do it that. And it is still pretty small. So are there any questions about the ternary operator given the context of this explanation? The two absolute function implementation would do exactly the same thing, except one is longer. And someone's going to complain and go like, but Tech, you could have just returned something inside the then and the else branch. I just consider that not a very good programming style, to have anything that alters the execution path from inside the conditional statement or loop or any other control structure. In fact, personally, I think there should only be one single return at the very end of a subroutine. Yep.
Is there like a reason for that other than just it's tacky?
Tacky as in me, right?
No, as in like it doesn't look good. It's hard to follow if there's a lot of returns. Is that the
It has, well, okay, so in a very short subroutine, it is usually okay and you can still figure out what it means. But once you start that, it's a slippery slope. In other words, at which point, with what kind of complexity do you stop using a single return inside a conditional statement or any other control structure to return directly to the caller? Do you see what I mean? So if your subroutine is really short, sure, I mean, you can still read it and understand exactly what it means. But if it gets a little bit longer, is that too long? If it gets even longer, is it too long? So at which point is the complexity of the subroutine sufficiently complex that it is not a good idea to put a return inside the control structure? Because the moment you do something like this, what about a return inside a while loop? Let's say you're trying to find the index of the first element with a particular value, okay? So you can do it inside a while loop, right? Because you can just, inside a while loop, you can say if x bracket I equals to k, which is what you're looking for, then return I, right? But you can do it inside the loop. you're doing it inside the conditional statement that is inside the loop. That seems to be a very good idea at the time because, hey, the code is a lot shorter, easy to, I can see exactly what's going on. But when you look at the loop itself, okay, by the time you get out of the loop, when you cannot find the value, then you say return false or return whatever value that indicates that you cannot find that index. But that is kind of really hokey because that defeats the whole purpose of a loop. The whole purpose of a loop is in order to get out of the loop, the while condition has to be false. But by using a return statement inside a loop, you're making that you're breaking that rule, which also makes the analysis of the code a little bit more funky later on because now you cannot only rely on the condition of a loop to decide, oh, by the time I get here after the loop, this condition has to be true. In other words, the negation of the while condition has to be true. But that doesn't apply anymore when you can have breaks and returns inside a loop. So that's me, just me, being strict about this type of programming, so I don't even start with a slippery slope. I don't grade by programming style at all in all of my classes. And if someone chooses to use labels and go-tos and whatnot, I'm not going to stop someone from torturing himself or herself. I do not extract enjoyment from that either, but it's none of my business. But if you ask me, how I code, this is the reason why I do not put returns inside the control structure, nor do I use break statements or continue statements, because it makes the analysis of the code kind of more difficult. All right, so getting back to here. So can we understand this code now? I mean, can we understand what is happening with this function? Okay, let me give you some examples. What if x is 5? Tell me what the function is going to return when x is 5. 5 is greater than or equal to 0 is true. So which expression becomes the answer? The second one or the one in the middle, which is 2x. So 10 is the answer. What if I give it negative 5? Negative 5 is greater than or equal to 0 is false. So we go for the false expression or the else statement, which is negative 2x, which is negative 10, minus 1. That will make it negative 11. Oh, sorry. Yeah, because x is negative 5, so this becomes 10, so it's just 9. Non-negative, positive 9. Is that okay? So what we are doing here is we are looking at the number line, okay? So if you look at the integer number line, kind of like this, and me being 0, okay? What I'm doing is I'm stretching out, but I'm also folding the negative side onto the positive side. If you are to, okay, do you guys want to see this in the spreadsheet? Because that's one really cool way to visualize and learn something about spreadsheets. I really need to ask administration and say, if someone passes this class, can they automatically get like a passing grade in our spreadsheet classes? But spreadsheets are extremely useful, not only for demonstration purposes. It's also really useful for many other things that you need to do on a daily basis. All right, so this is CISP 440. I'll put it into the shared folder. So right here, anything that I create here is automatically available to you. So I'm going to go new spreadsheet. And then we'll name the name the spreadsheet accordingly. So we'll name the spreadsheet. Okay, come on. Aleph. No. Integers. Okay, there we go. So what we'll do is we're going to have x on one column, and then we have f of x in the other column. And just for illustration purposes, we'll start with -10 with x. And then this one is really just the equation, plug in here. And then now we have the bigger question. Do we actually have ternary operators in the spreadsheet? The answer is yes. It is called an if expression. So when you type in the if expression, it's kind of the same structure. The first thing is a condition. So we have to enter the expression of, is this number less than 0? Is A2 less than 0? If the answer is yes, then we have to specify what we're supposed to return. So if that is less than 0, we are supposed to return, let me just be consistent with the notes, okay? If it's greater than or equal to 0, then we just return A2 times 2, okay? Double the original amount. If it is not the case, then we will do a arithmetic negation of A2 times 2 and then minus 1 from that. So now, this is actually doing exactly what, okay, let me magnify this a little bit so you can see better. View, zoom to 125, and when I click on the equation, you can see on the top, or if I double click, that gives you a better view. So this is doing exactly the same thing as the function that we mentioned earlier. If A2, which is x, is greater than or equal to 0, we just double the amount and that becomes the return value. If A2 is greater than or equal to 0 is false, then we return -2 times A2 minus 1. Okay, I just presented that a little bit differently, but basically the same thing. Is that okay? All right. So we press the enter key and it goes like 19. Okay, it sounds about right. And this is -9. There are several ways to do this. I'm just doing it the really lazy way. So once I select these two items and drag it on, the spreadsheet will figure out the pattern, and it will just kind of do it for me. Okay. And on this side, I'm just going to drag it down because I'm using the same equation for all of these, like so. All right. So when you look at the output here, you can see all the negative values are mapped to what? Odd numbers, okay? What about all the even numbers? Excuse me, all the non-negative numbers? They all become even numbers. Okay. So by doing this function, I am mapping integers into natural numbers. So now I have to ask myself a few questions. Is it injective? So here's a quick mini quiz, right? What is injection? Everything in the codomain is mapped to at least once. At the most once. At least once will make it surjective. So the idea of injection is no two elements in the domain should map to the same thing in the codomain. That's the other way to say it. Okay? So now the question is, well, what do you think about this function? Is it injective? If I have two different values, are they guaranteed to map to two different natural numbers? Yes. Okay, cool. Is it surjective? Now that becomes a little bit harder, right? In other words, is everything used in the codomain? Can I find a number in the codomain and go like, yeah, nobody maps to this guy? Well, all we have to ask is it an odd number or is it an even number? If it's an even number, you divide that number by 2, and that becomes the number that maps to that value. If it's an odd number, you add 1 first, then you divide it by 2, and then you negate arithmetically. That becomes the negative value that maps to it. So it is injective and surjective. Okay, well, if it is injective and surjective, it also guarantees an inverse function. In other words, I can write another function that reverses back to whatever we started off in the first place. Okay. So let me switch back to the notes here. Okay. So when I switch back to the notes, it has some detailed discussion of why we think this function is injective and surjective. And then here's a little bit of a proof. And here we have the inverse function. So mathematically speaking, when you say the inverse function, it is f, which is the name of the function, and then to the power of -1, quote unquote. That's basically what we use to denote that this is the inverse of f. Okay, this is the inverse function of f, and it has a single argument of x. So this time, it is still a ternary operator, but this time we are using x mod 2 equals to 0 to determine whether x is even or not. If x mod 2 equals to 0, x is even, otherwise it is odd. What if it's an even number? We just divide it by 2, and that becomes the integer that mapped to this natural number. What if x is odd? Well, we add 1 to it first, and then we divide the whole thing by -2, and that will map to the negative integer that maps to this natural number, x. Yep. Okay. So now that we have illustrated that I can have at least one function that is both injective and surjective, it takes all the integers as the domain, and it takes all the natural numbers as codomain, and it is bijective. What is the significance of that? You can read the last paragraph. Because f is bijective, because it is both injective and surjective, it follows that now we can claim that n and z, or the set of all natural numbers and the set of all integers, have the same cardinality. That is how we compare cardinality between sets that have an infinite number of elements. Is to ask the question, can you make a function that is bijective from one set to the other set? If it's bijective, you're guaranteed an inverse function, so the other way around is going to be true as well. Is that okay? It's kind of like asking the question between Tak and George. Okay, so you can say is Tak and George equally wealthy? Okay, and then the criteria is to say, well, let's count their gadgets. Okay. If for every single gadget that Tak has, George has an equivalent gadget, and vice versa, we'll call them equally wealthy. Yep, I got multiple multimeters, soldering stations, and whatnot. I don't know what George has, but he might have some other gadgets. Is that okay? All right. Now, this is also interesting because we can also count any set at all, as long as you can define a bijective function to map to natural numbers. All of those sets can be said as infinitely countable, which is kind of strange, right? If it's infinite, is it really countable? Well, that's what it is. Let me say that one more time. If you give me a set, okay, that naturally has an infinite number of elements, and I can give you a bijective function to map from the set that you gave me to the set of all natural numbers, and that function, once again, has to be bijective. As long as at least one such function exists, then I can say the set that you just gave me as infinitely countable. Is that okay? It's basically just a term, but it is an important term. So now, with this out of the way, I'm going to show you something else. And basically, we are looking at two-dimensional coordinates. And then we ask, is the set of all two-dimensional coordinates, and we have that restriction of each coordinate only has two components and they're natural numbers. Okay, so 0, 0 is one coordinate. 5, 16 is another coordinate. Okay, they don't go negative. It's just so each axis is a natural number. Is that okay? So if I were to draw a picture, I can't get my tablet to work yet in this semester, so I kind of have to rely on the whiteboard. So the question is, if I have a coordinate system where the x-axis just go like 0, 1, 2, 3, 4, and then y-axis do the same thing, 0, 1, 2, 3, 4, and I look at the coordinate, all the possible coordinates as one set, okay? Is that set countable? It's definitely infinite, but is it countable? Can I map all of these coordinates into the set of all natural numbers? What I'm really asking is to ask, can I find a function g, okay, so let's not use f anymore. Can I find a function g such that natural number Cartesian product with natural number as one as the domain, map it to the set of all natural numbers? Well, the function is not difficult to find, okay? Because you can always say, oh, I can make a function like that. G of xy is a constant of 0. That will meet the requirement of being a function. Once again, what is the requirement of being a function? From the set perspective, what makes a particular set a function? Exactly. So every element in the domain must be mapped to one and only one element in the codomain. Well, do you think 0 depends on xy? No. So that means every single element in this set, the Cartesian product of two natural number sets, they all map to one single element in the natural number set. Well, that meets the requirement. But does that mean the set of all coordinates in 2 dimensions is countable? Nope. It doesn't mean it's countable. So this is way too easy. All right. So how are we going to count numbers in a 2-dimensional system in a way that it is easy for us to see, oh, okay, we can just keep counting this way, and the function itself is bijective. So the way to do this is easy. You might want to write this down, even though it's kind of in the notes, too. You might want to write this down. Okay, location or coordinate 0, 0 is mapped to the natural number of 0. The coordinate of 1, 0 is mapped to the natural number of 1. The coordinate of 0, 1 is mapped to the natural number of 2, and then 3, 4, 5, 6, 7, 8, 9, and then we got 10, 11, 12, 13, 14, and so on. Okay. So you look at the way we filled in, the space of this table. So the next question is, well, without getting the closed form of this function, do you think this function is bijective? So let's revisit what I mean by bijective. It has to be both injective and surjective. Injective means if you give me 2 different coordinates, I guarantee they will map to 2 different natural numbers. Is that true? Just intuitively. Seems kind of true because I never reuse the same number. It keeps counting up. Okay, what about the other way around? If I just give you a number, I can always find some place within this 2D space that number has to go to. It might take me a while to find that place. Like if you ask me, where's 600 in this picture? Well, it might take me a while because I have to go like, okay, next one is 15, 16, 17, blah, 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 blah. But eventually, I will find out where 600 is supposed to go in a 2-dimensional space. Does that make sense? So intuitively, it seems to make sense that this function is bijective. And because this function g is bijective, it also means the cardinality of this is the same of the Cartesian product of natural numbers is actually the same as the cardinality of natural numbers. Let me just write it down here. The cardinality of the Cartesian product between natural number and natural number is the same as the cardinality of just natural numbers, which we call Aleph null. Yep,
Is it also the same cardinality then as
integers.
integers?
Yep, yep, exactly. With integers, we can kind of buy it, right? Because it's still a number line, it's still a line, one-dimensional. This one is a little bit harder to swallow, don't you think? Because we're talking about squared, right? But they're the same. Well, but since I can find that function, we have to make that conclusion. Yep.
And is that, what is that based on? Like, so you're saying because we can find a function, but what says that finding that function implies that?
That's the definition of infinitely countable, is if you find a function to map from some random set that you give me to the set of all natural numbers, and that function turns out to be bijective, that qualifies that set that is in question to have a cardinality that is infinitely countable. Otherwise, the cardinality is known as Aleph null.
Okay, so that's just defined.
It is defined that way, correct. But this is really kind of important because that's the whole basis of discrete math. What is considered discrete? Well, in the sense of technical mathematical stuff. What is discrete? It has to be countable. Real numbers are not countable. So we don't deal with real numbers in this class. Yep.
So can you actually write a mathematical function to go from the coordinates to?
I'm so glad you asked because I spent a lot of time to figure that out. Because I don't want to, Okay, so this is really the same table as this, except it is kind of in a more linear fashion. Okay, so if you read that thing, we'll just pick one. Okay, g of 2, 1. Okay, g of 2, 1 is 2, 1, and that's 7. So instead of using a pictorial way to represent it, I'm just spelling out, in a particular sequence, what coordinate is mapped to which natural number. Is that okay? Does everybody see how this list here is really representing the same thing that's on the whiteboard, except the one on the whiteboard is just, a little bit more visual and easy to understand. Is that okay? All right. So now the question is, what is the closed form of this? In other words, if I say, I want to find out what is G, 2617, okay? How can I find that natural number? I know there's a natural number to map to that it maps to, but how can I find that natural number without actually having to spell out everything, right? Seems to be useful, right? If I can find a closed form, yeah, that would be cool. So how do we approach this problem? So the one thing we find out is g of x0 is always 0 plus 1 plus 2 plus 3 plus 4 plus, and so on, all the way up to x. Well, let's see if that makes sense, okay? We're talking about these guys, right? Where, x is moving, but y is stayed at 0. So we are talking about row 0 here. Okay, that's 0. We stop right there because, x is 0. X plus 1, 0 plus 1. 0 plus 1 plus 2. 0 plus 1 plus 2 plus 3. And then that plus 4, the next one is going to be what? What do you think? The next one is going to be plus 5 is 15. And then the next one is going to be 21, and then and so on. Okay? So this is also kind of the place where I can stop a little bit. Noticing the pattern is very important in computer programming. Okay? IBM used to have an aptitude test for programmers. In other words, they look at all the incoming employees and then they give people this particular aptitude test. And people who score well in that aptitude test typically will make very good developers / programmers. So you might want to dig up, those tests because, it really is testing. It's not an IQ test, okay? So do not look at it as an IQ test. It is a test of whether you can figure out patterns with numbers, shapes, and stuff like that, okay? And that tends to be an indicator that people use to predict success as a developer or slash programmer. Now, what if I am not good at these things at all? I'm not good with numbers. Does that mean I have no future in the computer industry? Nope, nope, not at all. What kind of talent do you think computer industry needs? Have you guys heard of UI UX? What is UI? User interface, and UX is user experience. Very good. Now, if you ask me, okay, UI UX is not necessary. Okay, if I can work with those really old VCRs, okay, many of you are too young to know what a VCR is, but if I can program those VCRs without a manual of all brands, okay, I think I can figure out how to navigate in a website. I like that comment. So, but these days, because websites, Android apps, they're not only for programmers. They're not only for people who work with computers. They're for everybody, right? So how do you make a website easy to navigate? Why is that even important? They will figure it out. Well, think about Amazon versus B&H, okay, which is a company in New York that sells electronics. Whatever website is more user-friendly, guess what? They get more customer. Okay, and customers spend less time to look for the product they want, which means they might order more. They're not going to give them go like, oh, I guess Amazon doesn't have this product, because you have to kind of drill really, really down to find it. But if B&H says, hey, give me some of these criteria and I'll help you search for products of the same category and then zero down to the one that you want, then you probably will order from B&H because you can at least find the product within a reasonable amount of time. So that means UI UX is a big deal. Okay, it's not only because we can make it more user friendly. No, it means hard code cache. Okay, do you think I would make a good person to evaluate user interface, user experience? No. The answer is just as solid, no. Okay. So people who do not work well with numbers or find patterns in numbers, they tend to be better candidates to figure out, oh, a person is not going to look at this and find what they're supposed to look for. You need to redesign it this way and this way and this way. So that's just my little spiel on that sort of thing. And just to show you, IBM Programmer Aptitude Test. And you cannot find the actual files. I don't think anyone has actually encoded those into files. But what you can find are bitmaps. Okay, people have taken picture of those tests and have posted those things online. So just for fun, you can go ahead and take these tests and just for kakas. All right. So getting back to our boring stuff here. So we notice this pattern. So that means, well, it seems like, g of the coordinate x0. In other words, the double parentheses is not a typo. The outer parentheses indicates the boundary of the parameters. The inner parentheses is basically the coordinate itself. It's a two tuple. That's why it looks like it's double, but it's not, because the two pairs of parentheses actually serve different purposes. Okay, so that seems to be pretty useful, but what is this? I mean, this is still kind of expanding out a whole bunch of numbers. So how do I find g of, say, 200, 0? Yep. Exactly, but how do you know that? Sorry? Say that? One more time? Arithmetic sum. Okay. But did you learn that or did you derive that? You got exposed to it, right? Somebody explained to you and go like, okay, this thing, can be expressed in a closed form, like that. Okay. But what I want to do in this class is to explain. Let's say you have never have any exposure to arithmetic sum. How do you come up with the closed form for something like this? So there are two cases. So first of all, think about two cases. Okay, this is going to be ugly. Okay, think of the two cases. The first case is, what if x is odd? Okay, so think about x as an odd number. 3 is an odd number, right? So we have 0 plus 1 plus 2 plus 3. How many terms do we have? 4 terms, right? When you add the first term to the last term, what do we get? 3. When you add up the second term and the second last term, what do you get? 3. So that's a pattern that you will notice is when x is an odd number, when you have an even number of terms because x is odd. That's because we start with 0. Okay? But then you will also notice that if you add the first item to the last item, it's one number. When you add the second number to the second last number, it's the same value. When you add the third number to the third number from the end, it will also be the same value. So that gives you an idea, go like, oh, okay. So, okay, let me see if I can use this to express that. So I would say when x is odd, okay, 0 plus 1 plus 2 plus blah, 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 x has x plus 1, the whole thing divided by 2 terms. Nope. Okay, I take it back. It has exactly x plus 1 terms. That plus 1 is because, we start from 0. Is that okay? But we also notice, but we can regroup things. We can say 0 plus x is one term, 1 plus x minus 1, which is the second last item, is another term, plus 2 plus x minus 2 is another term, and so on. What do you think is going to be the very last one in this case? Odd, remember, x is odd. Think of the special cases. Okay, what if x is 3? The very last term is going to be what? It's going to be x. So you will need to use division now because you have to kind of divide it by 2, right? What is 1 to 3? That's a really bad question. What is 1, 2, 3? What is 1 relate? How does 1 relate to 3 in the series of 0, 1, 2, 3? Okay, it's the floor of x divided by 2, right? Because 3 divided by 2 is 1 point something. You take the floor of that, that's just 1. Okay, so that becomes one term. And what about the other term? Let me see if I can scroll this over a little bit. Plus the floor of x divided by 2 plus 1, which is our 2. Or you can also know it as, x plus 1, the whole thing divided by 2. Okay? And how many of these terms do we have? This is one term, this is one term, this is one term, this is one term. How many of these terms do we have? Once I group the first with the last, second with the second last, and so on. X plus 1 divided by 2, right? Okay, all right, so that means, okay, I'm using the cursor key here. So that means, we know all of these add up to x, don't we? What is 0 plus x? X. What is 1 plus x minus 1? X. 2 plus x minus 2? X, and so on. So I think we are fairly convinced that every single term, just has the quantity of x. But how many of x do we have? X plus 1 divided by 2. So that means the summation is just, x times x plus 1, the whole thing divided by 2. Well, that's the case for when x is odd. What if x is even? Well, when x is even, then you have one term in the middle that doesn't have anyone to pair up with, right? Okay, let's think about an even number, 4, okay? 0, 1, 2, 3, 4. 0 pairs up with 4, no problem. 1 pairs up with 3, no problem. What about 2 in the middle? Doesn't have anyone to pair up with, right? So that's a kind of like a separate case. So how do we handle the separate case and so on and so forth? That's where this math is coming in handy. So x mod 2 does not equal to 0. Basically, it's saying, is x odd or is x even? If x is odd, we look at this summation term. If x is even, we look at this summation term here. All right, so let's take a look at these summation terms and see if it makes sense or not. Okay? Can everybody buy this? 0 plus 1 plus 2 all the way to x can be simplified using the sigma notation, as we are summing where I goes from 0 to x, and we are only summing the term I itself. Is that okay? The sigma notation is okay, familiar, okay? So now I break it up and say, what if x is odd and what if x is even? So the true when x mod 2 does not equal to 0, it means x is odd. So this is the case representing when x is odd. All right, so what is it doing? It's just breaking up the sequence into two halves. The first half goes from 0, but not all the way to x. It just goes up to x minus 1 divided by 2. How do we know x minus 1 divided by 2 is not going to give us some fractional value? Because x is odd, okay? If I know x is odd number minus 1 has to be an even number divided by 2 is going to be a whole number. Not a problem. What about this guy here? X minus 1, the whole thing divided by 2, plus 1. Oh, that's just whatever is going to follow that one, right? And then this one goes all the way to x. So are we buying that this expression, the simple sigma notation, is just broken up into two halves like this? Yep, okay. So when you look at this one and this one, okay, let me use a mouse pointer. So when you compare this term to this term here, what did I do? I mean, how do we combine the two sigmas into one single sigma? What trick did I use to combine the two sigmas? You look at the last term here, right? This is x. So when I equals to 0, how do I get x back? What about x minus I? Okay, are we seeing this? When I equals to 0, this I is just this I, no problem. X minus I is the last I of the second sigma. When I equals 1, what happens? It becomes the second last item in the second sigma, and so on. So I'm doing the pairing, in using this trick. But once I have this, it's pretty easy. That's just, the summation of x. Actually, this is not a typo. I is gone. How come I is gone? I mean, I was here, and then the next one has no I in it anymore. So we are talking about this to here. Now, when you look at the index, it is the same. The sigma did not change. What I did was to simplify the expression. I plus x minus I is what? X. Does x depend on I? No. So that means I can now just look at this and go like, oh, we are really just counting how many times we're adding x. And that turns out to be x minus 1 divided by 2 plus 1, because I starts from 0. And that's why we have a closed form here. So now we are done with the case when x is odd. What if x is even? Well, when x is even, we're going to do about the same thing, except we single out one term, which is x divided by 2, because it doesn't pair up with anybody. Is that okay? So this is kind of the first half minus that thing in the middle. This part here is kind of the second half minus the thing in the middle. Then I do exactly the same trick, combine these two sigmas into one single expression. I look at this expression and go like, Can I do better than this? Well, as it turns out, we can use exactly the same trick. Get rid of I, it becomes just x, but this time we only have x divided by too many x's here, but we have this extra term of x divided by 2 kind of on the outside, and then I do a little bit of algebra, and guess what we get? The two sides become exactly the same. In other words, we didn't really quite need that ternary operator to begin with, because they both derive to exactly the same expression. So when you look at the very last line of this proof, it's just x times x plus 1 divided by 2. Now, I know many of you have some exposure to this summation having a closed form already, but I'm explaining how to derive it. How do you look at the series and go like, okay, how do we group these things, so that it has a closed form? Is that okay or not? Okay. Are you guys all familiar or at least comfortable with the sigma notation at this point? Okay. So that solves one mystery. In other words, now we know how to figure out these guys, which is one single row of the two-dimensional space. Then what about the other ones? Well, the other ones turn out to be really easy to figure out, because once you have a y that is non-zero, you just need to kind of add something to it. So what you need to do now is first find out which diagonal line you'd want to work with, find out where the base of the diagonal line is, figure out what the base value or the value at the base of that diagonal line is, and then just add y on top of that until you get to the coordinate that you want to find. That's a lot of words, okay? I myself is not an auditory learner, so I probably would have just tossed away everything that I just said if I were in your shoes. And that's why we're going to use a picture, right? Okay. It's really too bad that I can't get my tablet to work, to project it on the projector. I don't have a problem with if you guys want to take a picture of what is on the whiteboard. Just make sure that I'm not in the picture. That's fine. All right, so we'll go ahead and take a look at this, kind of horrendous thing, and we'll say 2317. Okay, this is the coordinate. I want to find out what natural number it maps to. Okay, that seems pretty hard. Okay, so we need to go back to the other picture and see if we can find a pattern. Okay, because what we want to do is to find a pattern of what is the one thing that is common to all the pixels of the same diagonal line. Okay, so we'll observe a few things. 0, 0 by itself as a diagonal line, doesn't give us a lot of clues, unfortunately. These two, let's see. This coordinate is 1, 0. The coordinate of this one is 0, 1. Okay, transposed. Okay, let's take a look at the next one. This one has a coordinate of 2, 0, 1, 1, and 0, 2. I think we're starting to get a pattern here, right? Let's check out the next one. The next one here, starting with a 3 here. This is 3, 0, 2, 1, 1, 2, and 2, 2. Do you see a pattern? Oh, not 2, 2, 0, 3. But what is the pattern? When you add the x and the y coordinate of the same diagonal line, they always add to the same sum. 3 plus 0, 2 plus 1, 1 plus 2, and 3 plus 0, 0 plus 3. They all add up to be the same. Oh, okay. But what are they adding up to? What do you think they're adding up to? The x of the g of x0. Okay? In other words, they're all adding up to the x coordinate of the element all the way at the bottom of that diagonal line. Isn't that something? Yes, it is. I'll answer that question for you. Yes, it is. Okay. So that is kind of cool because what I can now go back to this case is to say if I add 23 and 17, which adds up to what, 40, right? We are looking at 0, 1, 2, 3, blah, 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 and 40 is all the way over here. This is the base of the diagonal line where 2317 belongs. Cool. Is that okay? Because when you look at everything in this diagonal line, when you add the x and the y coordinates, they always add up to 40 because they're on the same diagonal line. Okay, wait. Okay, so that's good because now we can figure out the value right at the base at 40, comma 0. We can use that other equation that we figured out earlier, right? So this is 40 times 41, the whole thing divided by 2, which is 20 times 41, which turns out to be what? 820? 820, right? Okay. So right at this cell here, this is 820. Oh, I already divided by 2. Yep. Okay, so it's 820 at the base. Great. Okay, now we know the value at the very base of the diagonal line. What about the coordinate that we are at here? Look at the y. It's 17. The next one is going to be 821, 822, 823. The higher the y value, the more we add to the value at the base. So can you guess what this number is going to correspond to? 820 plus 17, which is 837.
Didn't you do the point 2017 in your calculations, though?
Huh?
You did the point 2017 in your calculations, no? So the formula is x times x plus 1 over 2. So you did
Yep.
20,
So this is x
which is,
plus x times x plus 1,
yeah.
and then the whole thing divided by 2.
I thought we were doing it at 2317.
23 plus 17 is 40. So you find the base of this diagonal line. So this has the coordinate of 40, comma 0. Right? So once we find this one, we can figure out the value for this guy because that's just the simple sigma notation. And then we have the closed form of the sigma, which is x times x plus 1, the whole thing divided by 2. And then we use that to go back and figure out the value corresponding to the pixel that we are interested in. Is that okay? So if I want to generalize now, what is g of xy? Okay, so I'm going to introduce an intermediate term first, okay? So I'm going to introduce an intermediate term, I'm just thinking about what to call it. Let's call it m, okay? So I'm going to say m equals to x plus y, okay? Because that will tell me what is the x coordinate of the base of that diagonal line. Is that okay? So now I will say this is the same thing as, okay, extra parentheses, I forgot about that one. So we'll expand this one and go like, oh, this is really the same thing as m0, which is the base of the diagonal line or the value of the base of the diagonal line, plus whatever y is. Is that okay? And then from the earlier equation, we know that g of, in parentheses, m0 as a coordinate, is really just m times m plus 1, the whole thing divided by 2. That's coming from the simplification of the sigma notation. Question? And then plus y. Okay. But what is m? Well, we have to kind of re-expand m. M is x plus y. And then the other m is also expanded to x plus y. But this time we have to add 1. The whole thing divided by 2 plus y. So that's the closed form that will map us from a two-dimensional coordinate to a single natural number. And I thought this is kind of cool, but it's not cool until we can prove that at least validate that it works, right? So how are we going to validate this? Because I can spew out any type of equation here, and there may not be a whole lot of people that can, say, "Tack, I think you got a mistake here." So how do I catch my own mistake? Yeah, sure. Yeah, so 17 and 23, x plus y is 40. X plus y plus 1 is 41 divided by 2. So I just do the simplification. So that becomes 20. 20 times 41, and then plus the y, which is 17. So that should come up with 837, because this is how we got to this generalization. But we can plug this into this thing here, right? Because this thing here is pretty solid, because I just did the manual counting. But instead of doing that, because I'm really bad with arithmetics, I'm not going to do it. So can anyone guess what I'm going to do to check my own equations? Starts with the S. Spreadsheet. The mighty spreadsheet is going to help us here. All right, so what I'll do is I'm going to have to explain a little bit. So we'll say column A is 0, okay? We'll say that column 1 is also 0, okay? That's just the way I count here. Is that okay? So this is basically the cell A1, this is the cell B1, and so on, okay? So we'll take a look here, and we have to plug in that equation. So the equation is the row number minus 1 plus the column number minus 1 times the same thing, row number minus 1 plus column number minus 1 plus 1. So basically row number minus 1 is giving me the y coordinate, column minus 1 is giving me the x coordinate. So this part is y plus x, y plus x plus 1, okay? And let's see, did I use, I need an explicit multiplication symbol because it doesn't understand the shorthand. And then we have to divide the whole thing by 2. But wait, there's a little bit more because we have to add the y coordinate. The y coordinate is row number minus 1. The reason why I have to subtract 1 is because row number starts counting from 1 and not 0. So that's why I have to offset everything by 1. Is that okay? Cool. Enter 0. Do you think I should stop now? Now that I'm ahead, just kind of like stop when I'm still ahead. That would be a great strategy at a casino. All right, so let's check out the first row. Okay. Do these numbers look familiar to you? 0, 1, 3, 6, 10, and the next one's going to be 15. That's exactly what we got. So now we'll expand it vertically. Yeah, like so. So I know it's a lot of numbers, but we'll just kind of check the corner, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It seems to be following that diagonal line of counting. All right, so if we are to find out where 837 is going to be, I think it's doable because all we need is 17 rows and 23 columns. That's doable. Let's do it. Sounds kind of fun to me. All right, so we'll expand it to 26 this way, and then we'll expand the other way to z. That would be 26 of those. And we want to find what number again? 837. So 837 is right here. So we have 18, which is the y coordinate, but it's off by 1, remember. So what we read as 18, row 18 is actually 17 when we count from 0. And then you look at x, so you have to remember, how many letter is x away from A. Okay, x is the third last letter out of 26, right? So 26, 25, 24, and then you have to subtract 1, which is our 23. So seems to work out. But the outcome of this is profound, because it basically means if you need to transmit if you need to transmit two numbers as a coordinate, okay, there's a way to transmit a single number as long as the other side knows that that one single number is actually representing a two-dimensional thing. Is that okay? But because this function, as we we intuitively think that it is bijective. Let me explain again why we think it's bijective. It's injective, which basically means if you give me two different coordinates, I think they have different values. Seems to make sense because we are assigning sequential numbers, so we will never use the same number again, right? What about the other way around? If I just randomly point at one location in a two-dimensional space, does that space have a value? Does it map back to a does it always have a natural number mapped to it? Yeah, because using this way, I can fill up the space to any pixel that I want. Okay, so it's bijective. Now, if it's bijective, that means there has to be an inverse function, right? If I just throw the number to you and go like 837, where is it in a two-dimensional space? There should be a way to reverse that, other than this really kind of awkward way of looking through a big table and look for the number that we want to look at, that we want to find. So the rest of this note is how to figure out the inverse function. So if you continue with this, blah, 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 then the inverse function is all the way at the bottom. So okay, we only have 5 minutes left, so I'm not going to go through all the pine needles. So instead, I'm going to I'll take one step back. We'll look at the pine tree, okay? The pine tree is, if you give me a natural number, I can find out what is the coordinate in the two-dimensional space that will give me that natural number to begin with, okay? Yeah, it looks kind of ugly because it has got a floor on top of, square root and stuff like that, but it is a function, okay? So why is it profound? What if we have a three-dimensional space? So we got x, y, and z. What are we going to do about that? Okay, so let me pose this question. So we have three-dimensional space here, okay? And I ask, what is the cardinality of that? Does it or does it not equal to aleph no? What if it's four-dimensional? What if it's five-dimensional? And so on. They're all aleph no. Because what we have discovered with this function of g is a way to fold a two-dimensional space into one dimension. So what if we start up with 3? Fold these two first into one single dimension. That one single dimension is a natural number dimension. Then you fold that with the third one into one single dimension. So I can now fold any number of dimension as long as the number of dimension is fixed into the natural numbers. And it's bijective. It's kind of cool in a way because, let's say you and your friend have some kind of, secret communication that you need to do, okay? And you need to disclose, like 6 numbers, okay? So there are 6 numbers that you need to communicate with your friend, but you don't want anybody else to find out, what those 6 numbers are, okay? So now you can fold the 6 dimensions into one. It becomes one pretty big natural number. You send that one single natural number to your friend. That your friend, knowing exactly how the spaces are folded, will unfold it back into the 6 individual numbers that you encoded in the first place. I think just conceptually that's kind of cool. In terms of practicality, probably, maybe not too practical. What do you think? Huh? Not only the total number of dimensions, but they also need to know how they're folded. Because you can choose any 2 dimension to fold, and then which 2 dimension to fold and which 2 dimension to fold. So that ordering is important. If you and your friend did not communicate clearly, how the 6 dimensions are folded into one single dimension, your friend could have used the wrong decoding method and come up with the 6 numbers in the wrong order. I believe it will still be the same 6 numbers, but the ordering would not be correct. But nonetheless, we can map anything that looks like this, as long as we know ahead of time the number of natural numbers in the Cartesian product. They all end up with Aleph null, which is very, very counterintuitive, because if you think about it, it doesn't seem to make sense. How can a multi-dimensional space where each dimension is a natural number still end up with a natural number? We can still count it as natural numbers. Yep. That's a very good question, and I would say it is not unique. I mean, if you think about all the mapping, this is just one that's easy to express, but you can have some really randomized mapping pattern that has no particular pattern, there's no closed form to talk about, but it will still be a one-to-one map. This is just one that is easy to deal with from our perspective. That's a good question. So are we okay with this slide or this module? So what I want you guys to do, we got 2 minutes left, is to read the module, okay? Read the module the way it is intended, which means I'm explaining how the terms are derived, okay? Because by reading that, I'm hoping that you will actually get to the essence of this class, which is kind of like, why is math important in computer science? Why is it contributing? Because if you just look at the summary of all the proofs, okay, it's just a conclusion. But how do I get to that conclusion? I think that is more important than the conclusion itself. The mechanism to arrive to the conclusion, in this class at least, is more important than the conclusion itself. It's not the knowledge that is important, it is the meta-knowledge. How do you know, how do you gain knowledge? That becomes more important. But that's just my humble opinion. You can disagree. As I always say, I'm skeptical, but I'm also skeptical of my own skepticism. Yep. All right, so I'll see you guys on Wednesday, but please, try to dig this through. I know it's a lot of reading, but now that you understand the context, hopefully you will find reading the module a little bit easier.